This begins chapter 13 of James Stewart's, even though I call him James Strong later on in this video, sorry. It's actually James Stewart, and this is the beginning of his chapter 13 of his calculus textbook, Vectors and the Geometry of Space. And this particular video is on three-dimensional coordinate systems. I think you will find this section refreshingly easy, simple, and predictable. Enjoy. So you remember the good old days where we had a two-dimensional coordinate frame, an XY coordinate axis. This is named after René Descartes, a Cartesian coordinate frame. And now, however, we want to talk about a third dimension, which we're going to have coming out like this. Now, this is not the way that it's generally drawn in three dimensions. In fact, the book talks about a right-hand rule. So we're going to have the x coming out here and the y coming out here, and the z is going to be up and down. Okay, so this is going to be the way we're going to do it in three dimensions. We're going to have the x coming out of the board, as it were, the y going this way, and the z going up. Okay, now there's a right-hand rule they talk about in the book, where the z is the thumb going up, and then these are the positives. So this direction's positive, and this direction's positive, and that direction's positive. So the dot, dot, dot going that way is negative, or into the board is negative, or down is negative in three dimensions. Now we can now talk about planes, not planes, but planes as in flat planes. So the XY plane is basically the two-dimensional plane that is created by the cross section of the x and the y. We can also have, however, a XZ plane, which is kind of like that. And then we can also have a ZY plane, which would be something like that. And of course, even though I'm boxing it, it's not boxed. So as it were, this we have a little room here. Let's say that this is a room. This might help you. I think they have a couch drawn here in the. Well, it's a horrible couch. Let me draw a couch. Where you have a couch. Can you see it? So in this room, and this room here, you might call an octant. Remember quadrants? Remember when we were back in the good old two-dimensional world? This was the first quadrant, this was the second, the third, the fourth quadrant. Why quadrant? Because quad means four. And so there were up to four kind of ranges for two-dimensional. But in three-dimensional space, we have four. So we have this, so think of it, my son said, think of it as an apartment complex. So it's a 8-room oct means 8. Octopus has 8 arms. So this is the front top room. But there's also, there's a room over here. I'm not sure exactly how they're usually numbered, but we have a room here, and then back over here there's a room, and then back over here there's a room, and then there are 4 more in the basement, in the negative space. And so octant is like quadrant. Quadrant, we had 4. Now in three-dimensional space, we're going to have octants as we draw out these planes, and we have 8 different spaces. So another concept in this section on three-dimensional coordinates is the idea of the projection of a point. So let's say I have a point that's, it's 3 or 4 out on the x, and it's, 3 out in the y, and then it's a certain number up in the z. It's hard for me to draw because that looks like it's in the YZ plane. But let's imagine that it's actually out a little bit from that plane there. So the projection, I can project this point P onto any of these planes. So if I project it onto the XY plane, let's say it hits here at the XY plane. It's hard to draw in three dimensions. Let's call it point Q. Q then is the projection of P on the xy plane. I can also project P onto the xz plane. Let's say it hits right there. Let's call that R. Then that's the R is the projection. R is the projection of P onto the xz plane. And of course, then I can project it onto the yz. Let's say it hits here at S. And I can say then that S is the projection of P onto the YZ plane. Tucked into this first section of the chapter is some set builder language also. What is that? Set language. Mathematics gone wild with set theory. Basically, when we were doing two-dimensional stuff back in the good old days, before we hit three-dimensional space, you would basically, this symbol here, R, I think, refers to the set of real numbers. R squared it means two-dimensional. R times R means we have, for the x component, we have all the real numbers as possible elements, and for the y, we have all the real numbers as possible elements. So R times R, refers to all the possible ordered sets. The set of all ordered pairs that relate to two-dimensional space is denoted by R squared. And so the way you would write that is R times R basically is the set of all ordered pairs x and y such that x and y are elements of the real number set. Again, what? No point. There's no worry about this. This is just stuff. It's a symbolic language, a math language that if you be a math major, you would want to understand this more thoroughly. So we can now extend this to three-dimensional space, to where R cubed is the set of all ordered triples that relate to three-dimensional space. Okay, and so we write that R times R times R. So all of the x components that can be any real number, and all of the y components that can be any real number, and all of the z components that can be any real number. And so R times R times R is the set of ordered triples, x, y, and z, such that x, y, and z are elements of the real number system. Again, completely ignore this slide if your response is, what? Because it's not really important to life, in my opinion. Okay, but so we are talking in this video about a three-dimensional rectangular coordinate system. These are definitions. Now back to something that's actually helpful. The distance formula in 3 dimensions. So remember the distance formula in 2 dimensions? That was great. Basically, the difference between the x components of 2 points squared plus the distance between the y components of 2 points squared. Take the square root of it, and you have the distance between those 2 points. This is basically the Pythagorean theorem. A squared plus b squared equals c squared. And so this is the a squared, and this is the b squared, and then the square root of it is c, which is the line between the 2 points. Now, the extension of the distance formula into 3 dimensions is very predictable. You can guess it. Go ahead, guess it. You know it. It's on the tip of your tongue. You just add the z component. Ta-da! And so this is the distance formula in 3 dimensions. So you remember from analytic geometry what the equation of a circle is. So let's say that you have a circle of radius r whose center is at the origin. So what is the equation of this circle going to be? It's going to be x squared plus y squared equals r squared. You remember that from the good old days back in analytical geometry in the 11th grade maybe? So that's nice and easy. Now, you also then in analytic geometry learned an equation for a circle if its center wasn't at the center. You remember this? X minus h squared plus y minus k squared equals r squared. You remember that? That's where the center of the circle is at h, the point hk. Now we're going to do spheres. So in 3-dimensional space, we still have for a sphere, a radius r out from the center. Except now, we're not just going to draw that around a two-dimensional, we're going to draw it around a three-dimensional, and I'm not going to be a good enough drawer probably to do this, but I'll try. So now we're talking about a sphere, where if you rotate that R around all three dimensions, you're going to get a sphere. And the formula for a sphere is actually quite logical, given the formula of a circle. So if that sphere's center, if the center of the sphere is at the center of all this mess, then that's going to be the formula. And as you've already guessed, then the equation for a sphere, if its center is not at the center, it's going to be x minus h squared plus y minus k squared plus z minus l squared equals r squared, which it's just basically an extension of the very same formula for a circle that you learned in analytic geometry. And that's pretty much the end of this particular section of James Strong's calculus textbook.